Imagine a sky full of stars, where you can not only see a backdrop of shining lights, but also discover the hidden tale of a cosmic saga. Or think back to when the universe was a chaotic, wild place, and from there, a big galactic formation was born, the Milky Way. Stardust, also known as space cruising, is a voyage through the intricacies of time and space, unraveling the mystery of how our galaxy, a whirling disk of gas, stars, and dark matter, came into existence. In this video, we are going to imagine the birth of the Milky Way, which is a story of billions of years, starting from the first whispers of creation and ending with the famous spiral galaxy we call home today. It is as if we were hopping on a cosmic train and witnessing both close collisions of the Milky Way and stellar nurseries of the past. Be prepared for a time travel journey, see the evolution of the galaxy, and learn the amazing story of the universe we call home. Keep your seatbelts on, because this journey to the early years of the Milky Way will be a celestial adventure. The beginning of everything. In the vast expanse of the universe, the story of the Milky Way begins with the most profound event in cosmic history, the Big Bang. Approximately 13.8 billion years ago, all matter and energy in the universe were condensed into an infinitely small point, a singularity. This singularity was unimaginably hot and dense, containing all the potential for everything that would ever exist. Then, in a moment of explosive expansion, the universe began to inflate at an astonishing rate, marking the beginning of time and space as we know it. In the first fractions of a second, the universe expanded exponentially in an event known as cosmic inflation. During this period, the universe went from being smaller than an atom to the size of a grapefruit in mere microseconds. As the universe expanded, it cooled rapidly, allowing the fundamental forces of physics to emerge. Gravity, electromagnetism, and the strong and weak nuclear forces began to differentiate themselves, setting the stage for the formation of matter. Within minutes, the universe had cooled enough for protons and neutrons to begin forming, leading to the creation of the first atomic nuclei in a process called nucleosynthesis. These early nuclei were primarily hydrogen and helium, the simplest and most abundant elements in the universe. The young universe was a hot, dense plasma of particles and light, a cosmic soup where matter and energy were indistinguishable. As the universe continued to expand and cool, it reached a point where electrons could combine with these nuclei to form neutral atoms, allowing light to travel freely for the first time. This moment, known as recombination, resulted in the cosmic microwave background radiation, a faint glow that permeates the universe and provides a snapshot of the universe when it was just 380,000 years old. The universe then entered a period known as the Dark Ages, a time before the first stars formed. During this epoch, the universe was filled with dark matter and diffused hydrogen gas. Dark matter, an invisible substance that does not emit or absorb light, played a crucial role in the formation of the first galaxies. Its gravitational pull helped clump together the gas, creating dense regions that would eventually collapse under their own gravity to form stars and galaxies. It is within this dark, quiet, and mysterious phase that the seeds of the Milky Way were sown. The first stars and galaxies. As the universe emerged from the Dark Ages, it began to light up with the formation of the first stars, marking a new chapter in cosmic history. These first stars, known as population III stars, were fundamentally different from the stars we see today. They were composed almost entirely of hydrogen and helium, as the universe had not yet had time to create heavier elements. These stars were massive, often hundreds of times the mass of the Sun, and they burned their nuclear fuel at an incredible rate. Their short lives ended in spectacular supernovae, explosions that scattered the first heavy elements into the surrounding space. These early supernovae had a profound impact on the formation of the first galaxies. As the massive stars exploded, they created shock waves that compressed the surrounding gas, triggering the formation of new stars. This process, known as positive feedback, led to the rapid formation of star clusters and eventually small galaxies, known as protogalaxies. These protogalaxies were the building blocks of larger galaxies, including the Milky Way. The formation of the first galaxies was a chaotic and violent process. The early universe was a crowded place, with protogalaxies frequently colliding and merging with each other. These mergers played a crucial role in the growth and evolution of galaxies, including the Milky Way. As smaller protogalaxies merged, they combined their stars, gas, and dark matter, creating larger and more complex structures. This process of hierarchical merging is a key feature of the current model of galaxy formation, known as the lambda cold dark matter model. During this period of intense star formation and galaxy growth, the Milky Way began to take shape. The early Milky Way was a much smaller and more irregular galaxy than it is today. It was composed of several small protogalaxies that were in the process of merging. These mergers were violent events that could disrupt the structure of the galaxies involved, but they also provided the material needed to build a larger galaxy. As the protogalaxies merged, they created a larger and more massive galaxy, with a dense core of stars surrounded by a halo of dark matter. Building blocks of a galaxy. The formation of the Milky Way was a slow and complex process, taking billions of years and involving the merger of many smaller galaxies. As these protogalaxies came together, they brought with them stars, gas, and dark matter, all of which played a role in building the structure of the Milky Way. Dark matter, in particular, played a crucial role in the formation of the galaxy. Although it is invisible and does not interact with light, dark matter makes up most of the mass of the Milky Way and provides the gravitational pull needed to hold the galaxy together. The merging of these smaller galaxies was not a peaceful process. It was marked by violent collisions and intense bursts of star formation, triggered by the compression of gas during the mergers. These bursts of star formation created new stars and star clusters, adding to the growing mass of the Milky Way. The newly formed stars were not evenly distributed throughout the galaxy. Instead, they formed a thick, irregular disk that surrounded the dense core of the galaxy. As the Milky Way continued to grow, it began to settle into a more stable and organized structure. The gas in the galaxy cooled and settled into a rotating disk where it could form new stars in a more orderly fashion. This rotating disk became the precursor to the thin disk of the Milky Way that we see today. The stars in the disk are arranged in a spiral pattern, with the densest regions of gas and dust located in the spiral arms. These spiral arms are the sites of ongoing star formation, as the gas is compressed by density waves moving through the disk. The early Milky Way also had a thick, spherical halo of stars and dark matter that surrounded the disk. This halo was composed of older stars, many of which had formed in the protogalaxies that merged to create the Milky Way. The stars in the halo are much older and less metal-rich than those in the disk, indicating that they formed earlier in the galaxy's history. The halo also contains many globular clusters, which are dense groups of old stars that orbit the center of the galaxy in a roughly spherical distribution. The emergence of the galactic disk. The Milky Way's journey from a chaotic collection of merging protogalaxies to a structured spiral galaxy took several billion years and involved a series of complex and interrelated processes. One of the most significant developments during this period was the formation of the galactic disk, a defining feature of the Milky Way. The galactic disk is a flat, rotating region of stars, gas, and dust that forms the visible component of the galaxy, extending outwards from the central bulge. The formation of the galactic disk was driven by the cooling of gas within the galaxy's dark matter halo. As the gas cooled, it lost energy and began to settle into a rotating disk. The rotation of the disk is a result of the conservation of angular momentum, a fundamental principle of physics that states that the angular momentum of a system remains constant unless acted upon by an external force. As the gas in the Milky Way cooled and collapsed, it began to spin faster, just as a figure skater spins faster when they pull their arms in. Within the disk, stars began to form from the cooled gas. These stars were born in clusters, or groups, which formed in the densest regions of the disk. Over time, these clusters dispersed, and the stars became part of the larger stellar population of the disk. The process of star formation in the disk was not uniform instead. It occurred in regions of higher density, leading to the formation of spiral arms. These spiral arms are regions where the density of stars and gas is higher than in the surrounding disk, and they are the sites of ongoing star formation. The formation of the spiral arms is a complex process that is not yet fully understood. One of the leading theories, known as the density wave theory, suggests that the spiral arms are regions of higher density that move through the disk like waves. As these density waves pass through the disk, they compress the gas and trigger star formation. This process creates the bright young stars that make the spiral arms so prominent. Another theory, known as the self-propagating star formation theory, suggests that the spiral arms are formed by the combined effects of star formation and supernova explosions, which create shock waves that trigger new star formation in a feedback loop. The role of supernovae and stellar feedback. As the Milky Way continued to evolve, it was shaped not only by the forces of gravity and angular momentum, but also by the energetic processes occurring within its stars. Among these, supernovae explosive deaths of massive stars played a particularly crucial role. Supernovae are not just spectacular cosmic fireworks. They are also fundamental to the evolution of galaxies, including the Milky Way. When a massive star exhausts its nuclear fuel, its core collapses, leading to a dramatic explosion that can outshine an entire galaxy. This explosion, known as a supernova, releases a tremendous amount of energy and ejects the outer layers of the star into space. The impact of supernovae on the Milky Way was profound. The explosion's shock waves compressed the surrounding gas, triggering new waves of star formation. This process, known as supernova-driven star formation, is an example of positive feedback, where one event, a supernova, triggers a chain reaction of events, star formation, that amplify the original effect. In this way, supernovae help to regulate the rate of star formation in the galaxy, preventing the gas from collapsing too quickly and forming too many stars at once. In addition to triggering star formation, supernovae also played a crucial role in enriching the interstellar medium with heavier elements. During the explosion, the intense heat and pressure caused by the collapse of the star's core allow for the creation of elements heavier than iron, such as gold and uranium. These elements are then scattered into space, where they become part of the gas and dust that forms new stars and planets. Without supernova, the universe would lack many of the elements essential for life, including carbon, oxygen, and iron. Stellar winds, another form of stellar feedback, also played a significant role in shaping the Milky Way. Massive stars, even before they end their lives in supernovae, emit strong winds of charged particles that can have a significant impact on their surroundings. These stellar winds can blow away the surrounding gas, preventing it from forming new stars, or they can compress the gas, triggering new star formation. Stellar winds are particularly important in the early stages of a star's life, when they can influence the formation of planetary systems and the distribution of gas in the galaxy. The formation of the galactic halo. While the galactic disk and its spiral arms were taking shape, another component of the Milky Way was also forming: the galactic halo. The halo is a roughly spherical region that surrounds the disk of the galaxy, extending far beyond the visible stars. It is composed of dark matter, old stars, and globular clusters, which are dense groups of stars that orbit the center of the galaxy. The formation of the halo is a key piece of the puzzle in understanding the early history of the Milky Way. The stars in the halo are among the oldest in the galaxy, suggesting that they formed early in the Milky Way's history, before the formation of the disk. Many of these stars likely formed in the small protogalaxies that merged to create the Milky Way. As these protogalaxies merged, their stars were dispersed into the halo, creating a roughly spherical distribution of stars that surrounded the disk. The stars in the halo are much older and less metal-rich than those in the disk, indicating that they formed before the Milky Way had been enriched with heavy elements by multiple generations of stars. Globular clusters, which are found in the halo, provide important clues about the early history of the Milky Way. These clusters are among the oldest objects in the galaxy, with ages that date back to the early universe. They contain hundreds of thousands of stars packed into a small volume, and they orbit the center of the galaxy in a spherical distribution. The fact that globular clusters are found in the halo suggests that they formed early in the Milky Way's history, possibly in the small protogalaxies that merged to create the galaxy. The stars in globular clusters are also old and metal-poor, supporting the idea that they formed in the early universe. The formation of the halo is also closely linked to the presence of dark matter. Dark matter is thought to make up about 85% of the mass of the universe, and it plays a crucial role in the formation and evolution of galaxies. In the early universe, dark matter formed large, roughly spherical structures known as halos, which provided the gravitational pull needed to hold together the gas and stars that formed galaxies. The Milky Way's halo of dark matter extends far beyond the visible stars and plays a key role in holding the galaxy together and determining its rotation curve. The rise of the spiral arms. As the Milky Way continued to evolve, its spiral structure became more pronounced, giving the galaxy the familiar appearance we see today. The formation of spiral arms is one of the most striking features of disk galaxies like the Milky Way, and understanding how these structures form and persist is a key question in astrophysics. The spiral arms are regions of higher density within the disk, where stars and gas are more concentrated. These regions are also the sites of ongoing star formation, as the dense gas is compressed and forms new stars. The exact mechanism that creates and maintains spiral arms is still a topic of active research, but several theories have been proposed. One of the leading theories is the density wave theory, which suggests that the spiral arms are not fixed structures, but rather waves of higher density that move through the disk. As these density waves pass through the disk, they compress the gas and trigger star formation, creating bright young stars that outline the spiral arms. The spiral pattern is maintained as the density wave moves through the disk, much like a traffic jam on a highway moves through a line of cars. Another theory, known as the self-propagating star formation theory, suggests that the spiral arms are formed by the combined effects of star formation and supernova explosions. According to this theory, a wave of star formation begins in a region of the disk, and as the young stars evolve, some of them explode as supernova, creating shock waves that trigger new star formation in neighboring regions. This process creates a chain reaction of star formation that propagates through the disk, creating the spiral pattern. This theory suggests that the spiral arms are not permanent structures, but rather transient features that change over time as new waves of star formation occur. Regardless of the exact mechanism, the formation of spiral arms is closely linked to the process of star formation in the disk. The spiral arms are regions of higher density where gas is compressed and stars are formed. These stars are typically young, massive, and blue, making the spiral arms some of the brightest and most active regions in the galaxy. The ongoing process of star formation in the spiral arms is a key driver of the Milky Way's evolution, as it replenishes the galaxy with new stars and enriches the interstellar medium with heavier elements. The central bulge and black hole. At the center of the Milky Way lies a dense and mysterious region known as the galactic bulge. The bulge is a roughly spherical distribution of stars that surrounds the center of the galaxy, and it contains some of the oldest stars in the Milky Way. The formation of the bulge is a key piece of the puzzle in understanding the early history of the galaxy, and it provides important clues about the processes that shaped the Milky Way. The bulge is thought to have formed early in the history of the Milky Way, possibly through the merging of small protogalaxies or the rapid collapse of gas into the center of the galaxy. The stars in the bulge are old and metal-rich, indicating that they formed early in the galaxy's history, before the formation of the disk. The bulge also contains a significant amount of gas and dust, which suggests that it was a site of intense star formation in the past. At the very center of the bulge lies a supermassive black hole known as Sagittarius A. This black hole, which has a mass of about 4 million times that of the Sun, is one of the most intriguing objects in the Milky Way. The existence of a supermassive black hole at the center of the galaxy was first suggested in the 1916s. Based on the observation of high-energy emissions from the center of the Milky Way, over the past few decades, observations of the motions of stars near the center of the galaxy have provided strong evidence for the presence of a massive compact object, which is now known to be a black hole. The formation of Sagittarius A is still a topic of active research, but several theories have been proposed. One possibility is that the black hole formed from the merging of smaller black holes in the early history of the galaxy. Another possibility is that it formed from the collapse of a massive cloud of gas and dust in the center of the galaxy. Regardless of its origin, the presence of a supermassive black hole at the center of the Milky Way has a significant impact on the dynamics of the galaxy, influencing the motions of stars in the bulge and the distribution of gas and dust in the inner regions of the galaxy. Interactions with neighboring galaxies. While the Milky Way has been shaped by internal processes such as star formation, supernovae, and black hole activity, its evolution has also been influenced by its interactions with neighboring galaxies. The Milky Way is not an isolated galaxy. It is part of a larger group of galaxies known as the Local Group, which includes more than 50 galaxies, ranging from large spirals like Andromeda to small dwarf galaxies. One of the most significant interactions in the Milky Way's history is its ongoing interaction with the Large and Small Magellanic Clouds, two irregular dwarf galaxies that are orbiting the Milky Way. These interactions are causing the Magellanic Clouds to lose stars and gas, which are being pulled into the Milky Way by its gravitational pull. This process, known as tidal stripping, is contributing to the growth of the Milky Way, adding new stars and gas to the galaxy. Another important interaction is the ongoing merger with the Sagittarius dwarf galaxy, a small, elongated galaxy that is being torn apart by the gravitational pull of the Milky Way. The stars and gas from the Sagittarius dwarf galaxy are being pulled into the Milky Way, creating streams of stars that stretch across the sky. These streams provide important clues about the history of the Milky Way and its interactions with neighboring galaxies. These interactions are not just one-way processes. They also have a significant impact on the Milky Way itself. The gravitational pull of neighboring galaxies can trigger bursts of star formation as the gas in the Milky Way is compressed by the tidal forces. These interactions can also create tidal streams and stellar halos, which are groups of stars that are pulled out of the Milky Way and form long, thin structures that extend far beyond the visible disk of the galaxy. The future of the Milky Way. The Milky Way is not a static entity. It is a dynamic and evolving galaxy that continues to change over time. The future of the Milky Way will be shaped by a combination of internal processes, such as star formation and supernovae, and external influences, such as interactions with neighboring galaxies. One of the most significant events in the future of the Milky Way will be its collision with the Andromeda Galaxy, the largest galaxy in the Local Group. This collision is expected to occur in about 4 billion years, and it will have a profound impact on the structure of both galaxies. The collision will likely trigger a burst of star formation as the gas in the two galaxies is compressed and forms new stars. The gravitational pull of the two galaxies will also cause them to merge, creating a single, larger galaxy. This new galaxy, often referred to as Milkomeda or Milkdromeda, will likely be an elliptical galaxy with a more spherical distribution of stars and a less prominent disk. While the collision with Andromeda will be a major event in the future of the Milky Way, it is not the only factor that will shape the galaxy's evolution. The ongoing process of star formation will continue to create new stars and planetary systems, enriching the interstellar medium with heavier elements and driving the evolution of the galaxy. Supernovae and stellar winds will continue to regulate the rate of star formation, preventing the gas from collapsing too quickly and forming too many stars at once. The future of the Milky Way will also be influenced by the presence of dark matter, which makes up most of the mass of the galaxy. Dark matter will continue to provide the gravitational pull needed to hold the galaxy together, influencing the motions of stars and gas and determining the rotation curve of the galaxy. The study of dark matter and its role in the evolution of galaxies is one of the most important areas of research in astrophysics, and it will continue to be a key focus in the future. Understanding dark matter. Dark matter is one of the most mysterious and elusive substances in the universe, and it plays a crucial role in the formation and evolution of galaxies, including the Milky Way. Dark matter does not emit or absorb light, making it invisible to telescopes, but its presence can be inferred from its gravitational effects on visible matter. Dark matter makes up about 85% of the mass of the universe, and it is thought to form large, roughly spherical structures known as halos, which provide the gravitational pull needed to hold together the gas and stars that form galaxies. The study of dark matter is a key focus in astrophysics, as understanding its properties and distribution is essential for understanding the formation and evolution of galaxies. Dark matter is thought to be composed of particles that do not interact with light or other forms of electromagnetic radiation, making it very difficult to detect directly. However, its presence can be inferred from its gravitational effects on visible matter, such as the rotation curves of galaxies and the motions of stars and gas within galaxies. The Milky Way's halo of dark matter extends far beyond the visible stars and plays a key role in holding the galaxy together. The rotation curve of the Milky Way, which shows how the speed of stars and gas changes with distance from the center of the galaxy, provides strong evidence for the presence of dark matter. The rotation curve of the Milky Way remains flat at large distances from the center, indicating that there is a significant amount of mass in the outer regions of the galaxy that cannot be accounted for by the visible stars and gas. This mass is thought to be dark matter. The distribution of dark matter in the Milky Way is still a topic of active research, as understanding its properties and distribution is essential for understanding the formation and evolution of the galaxy. Some models suggest that dark matter is distributed in a roughly spherical halo that extends far beyond the visible stars, while others suggest that it may be more concentrated in the inner regions of the galaxy. The study of dark matter is a key focus in astrophysics, and future observations and experiments will provide important insights into its properties and role in the universe. The evolution of star systems. The Milky Way is not just a galaxy of stars and gas. It is also a galaxy of star systems, each with its own unique history and evolution. The study of star systems, including our own solar system, is a key focus in astrophysics, as understanding their formation and evolution is essential for understanding the history of the Milky Way and the potential for life elsewhere in the universe. Star systems form from the collapse of gas and dust clouds within the galaxy, a process that is driven by the gravitational pull of the gas and dust. As the cloud collapses, it begins to spin, forming a rotating disk of gas and dust around a central protostar. The gas and dust in the disk can clump together to form planets, moons, and other objects, creating a star system. The formation of star systems is a complex and dynamic process that is influenced by a variety of factors, including the mass and composition of the gas and dust cloud, the presence of other stars, and the effects of stellar winds and supernova. The evolution of star systems is also influenced by a variety of factors, including the interactions between planets and their host star, the presence of other stars, and the effects of stellar winds and supernovae. The study of star systems is a key focus in astrophysics, as understanding their formation and evolution is essential for understanding the history of the Milky Way and the potential for life elsewhere in the universe. The discovery of thousands of exoplanets, or planets outside our solar system, has revolutionized our understanding of star systems and has provided important insights into the diversity of planetary systems in the galaxy. The search for extraterrestrial life. The question of whether life exists elsewhere in the universe is one of the most profound questions in science, and the study of the Milky Way plays a key role in this search. The Milky Way contains hundreds of billions of stars, many of which have planets orbiting them, and some of these planets may have conditions suitable for life. The search for extraterrestrial life is a multidisciplinary effort that involves the study of planets, stars, and galaxies, as well as the search for signals from intelligent civilizations. The discovery of exoplanets has revolutionized our understanding of planetary systems and has provided important insights into the potential for life elsewhere in the galaxy. The discovery of potentially habitable exoplanets, or planets that have conditions suitable for liquid water, has provided important clues about the potential for life elsewhere in the galaxy. These planets are often located in the habitable zone of their host star, where temperatures are suitable for liquid water to exist on their surfaces. The study of the Milky Way also plays a key role in the search for signals from intelligent civilizations, a field known as the search for extraterrestrial intelligence. SETI involves the search for radio signals or other forms of communication from intelligent civilizations in the galaxy. The search for extraterrestrial life is a multidisciplinary effort that involves the study of planets, stars, and galaxies, as well as the search for signals from intelligent civilizations. The search for extraterrestrial life is a key focus in astrophysics, as understanding the potential for life elsewhere in the galaxy is essential for understanding the history of the Milky Way and the potential for life in the universe. The discovery of life elsewhere in the galaxy would have profound implications for our understanding of the universe and our place in it. Human exploration and observation. Human exploration and observation of the Milky Way have provided important insights into the history and evolution of the galaxy. The study of the Milky Way has a long history, dating back to ancient civilizations that observed the stars and planets in the night sky. The invention of the telescope in the 17th century revolutionized our understanding of the Milky Way and allowed astronomers to observe the stars and planets in greater detail. The study of the Milky Way has been greatly advanced by the development of new technologies, such as radio telescopes, space telescopes, and computer simulations. These technologies have allowed astronomers to observe the galaxy in greater detail and have provided important insights into its structure and evolution. The study of the Milky Way has also been greatly advanced by the development of new techniques, such as spectroscopy and astrometry, which allow astronomers to measure the properties of stars and gas in the galaxy. Human exploration of the Milky Way is still in its early stages, but future missions to other planets and moons in our solar system, as well as to other star systems, will provide important insights into the history and evolution of the galaxy. The study of the Milky Way is a key focus in astrophysics, as understanding its history and evolution is essential for understanding the universe as a whole. Reflections on our cosmic home. The Milky Way is not just a galaxy, it is our cosmic home, a vast and complex system that has shaped the history of the universe and our place in it. The study of the Milky Way provides important insights into the history and evolution of the universe and has profound implications for our understanding of the cosmos and our place in it. The Milky Way is a dynamic and evolving galaxy shaped by a variety of processes, including star formation, supernovae, black hole activity, and interactions with neighboring galaxies. It is a galaxy of stars, planets, and star systems, each with its own unique history and evolution. The study of the Milky Way also has important implications for our understanding of the potential for life elsewhere in the universe. The discovery of exoplanets and the search for extraterrestrial life have provided important clues about the diversity of planetary systems in the galaxy and the potential for life elsewhere in the universe. The Milky Way is a galaxy of star systems, each with its own unique history and potential for life, and the study of these systems is a key focus in astrophysics. As we continue to explore and observe the Milky Way, we are gaining new insights into its history and evolution, and we are uncovering new mysteries about our cosmic home. The study of the Milky Way is a journey of discovery. One that has profound implications for our understanding of the universe and our place in it. The Milky Way is not just a galaxy, it is our cosmic home, a vast and complex system that has shaped the history of the universe and our place in it. Thanks for watching this video.